My name is Joe Topjian. I'm from Calgary, Alberta, Canada. I work for an organization called Cybera. Cybera is the provincial NREN of Alberta. If you're familiar with NRENs and NREN communities, Canary would be the federal NREN. Canada has a provincial one in each province, and so I work for the organization of the Alberta NREN. That is my flight path here. And again, if you're familiar with the NREN community, this is a partial global view. You have a couple of the European spots on the right side. The dark blue on the left side, that would be the Canadian Research and Education Network. I'm the second from the left, and this is our provincial network. So this is the Alberta Research and Education Network. Along with providing network access, we have a couple of other services that we provide. One of them we call the Rapid Access Cloud, which is a free OpenStack cloud. Anybody in Alberta can sign up and gain access for a year. Technically, anybody in the world can. We just sort of monitor access, and we ask you not to use it if you're not from Alberta. So the items that I'm going to be covering today are just some storage updates of things we've done in the OpenStack cloud. Just a little bit of usage for the cloud. So this is a snapshot of the past 3 years. You can see we have 1,500 virtual machines running. It's not really a lot, but considering we have 2 people working on this cloud, and plus after a year, people are asked to leave the cloud, so there is a steady increase of it. Plus, this doesn't really get into the types of virtual machines running. It could be anywhere from a 1 gigabyte virtual machine, 1 gigabyte of memory, to 64 gigabytes of memory, and we have some other different virtual machines like GPU processing for machine learning and things like that. So if you're familiar with how to build a cloud, you have these servers that are called hypervisors. Hypervisors host virtual machines. Virtual machines go on individual drives or many different storage configurations. So virtual machines, everybody here probably knows the pets versus cattle. Treat your virtual machine like a cattle, so if it dies, then it's gone. But we tell users to store data that they really want on block storage volumes. So along with our virtual machines, we also wanted to offer a block storage volume service. And we decided to make that from a GlusterFS file system. So across all of the individual hypervisors, we took 1 or 2 drives from each of the hypervisors and turned it into a Gluster file system. Why would we want to do that? Because nobody else was doing it, and not in a way that nobody else jumps off a cliff, so you don't want to jump off a cliff, but because we really didn't find a history of anybody doing it, so we just wanted to see if it was really a good idea or not. Another reason why we wanted to do it, gave us converged compute and storage. We didn't have to have 2 sets of hardware for virtual machines, and we didn't have to have for virtual machines and for storage as well. It gave us resilient volumes. GlusterFS is normally configured in a way that makes data resilient. In this case, we had volumes stored. We had 2 copies of each volume stored throughout the cluster. And that sort of gave backup to when we told users, store important stuff on volumes. That just made it a little bit harder for the volumes to actually disappear or be destroyed some way. And the other benefit was that the block storage volumes appeared just as plain files on the underlying storage system. We like this because it's a lot easier to work with a plain file than it is with any type of non-file service. An example of that here, if you just ran the file command, it's just a QEMU QCal file that is attached to the virtual machine, just like a block device. They were thinly provisioned, so there's a 5 gig volume here, even though it's only taking up 600K of space. So these were all good and nice things about it. But the reality is that Gluster's weird. If anybody's worked with Gluster, they might know the same thing. And I should say that Gluster itself never actually lost any data. It never actually lost a volume or anything like that. We lost users' volumes in the beginning while we were learning how to use Gluster, but that was only for the first couple months or so. But just using Gluster day to day, it's just a bit strange. There aren't a lot of tools or documentation to really go into it. The log files are just really weird. So we weren't really comfortable with using it day to day. And then things like Elasticsearch, not Elasticsearch in particular, but applications like Elasticsearch, they would just kill part of our cloud. And the reason because of that is just the types of I/O patterns that were hitting Gluster, and then the fact that we had the converged compute and storage, so it would impact other users' virtual machines as well. So that between those two things, we weren't really happy with the service. So over the past year, we just ended up switching to a very generic LVM iSCSI block storage service. We ended up getting dedicated hardware for the block storage service. So instead of having it both on the hypervisors, we've now decoupled it into its own hardware. On that hardware, it's just they're just generic servers, but we load them up with a bunch of 3.5-inch disks. We configure it to use LVM that's exported via iSCSI. And the other thing we did, if you're familiar with OpenStack, we switched from using the VirtIO block device driver to VirtIO SCSI. A little bit more about that. VirtIO SCSI, the driver, it's configured on the OpenStack image itself. So on your OpenStack image, you put these hardware properties on there. The most noticeable thing is that your drives show up as dev SD whatever rather than VD whatever. And because of that, not because of the naming, but because they appear more like SCSI devices rather than a VirtIO device, MDADM and ZFS and things like that work much better. So we didn't really have the resiliency that Gluster had on the volumes anymore. We went to 3 individual volume servers. So the users are now responsible for basically backing up their own volumes, which means that if they were to attach a volume to the virtual machine, if they wanted that volume to be resilient, they should attach 2 volumes to their virtual machine, and they should use something like ZFS or MDADM to make their data more resilient. We thought this was a pretty good trade-off because if users really didn't care about the resiliency, then they could just attach 1 volume as normal. Or if they wanted to do some type of data resiliency in their own way, then they're more than welcome to do that as well. So I mentioned before that we have, per region in our cloud, we have 3 dedicated volume servers. So what happens if a user creates 2 volumes, attaches it to the virtual machine, but those 2 volumes are actually hosted on the same volume server? That volume server goes away, then they've just lost 2 volumes, even though we told them it would be safe. So OpenStack also has a feature called volume affinity. And what this does, you create a block storage volume, then you create a second block storage volume and say, no, don't put this on the same server that you just put that last one on. And since we have 3 block storage servers, you can do that for 3 different volumes. And then you can be sure that 2 of them can go away if you're mirroring on all 3 or something to that effect. It's a pretty cool feature. Future features, we would like to do encryption at rest on our block storage service. I was planning on doing this really soon, but I haven't found enough information on how safe it is to do. My main concern is that if we configure the block storage service to have some sort of encryption configuration, in 6 to 12 months down the road, that encryption configuration is changed. There's no upgrade path, and so we've essentially just bricked everybody's block storage volume. So that I'm still looking into and seeing if there is, right now a correct way of doing that. But speaking of encryption at rest, another feature that we offer in this cloud is an object storage service based on Swift. The Newton release contains support for encrypted objects at rest, and you can see how to do that if you just Google Swift encryption at rest. If you've worked with OpenStack Swift in the past, it's really simple to set up. The documentation is quite better than most other OpenStack services. There are some others that are really good as well. So we went ahead and configured this for our object storage service. And the reason why we did this, so the way that the object storage service is configured is you give the entire object storage service 1 master key. And then all objects that are uploaded to it are encrypted using this master key. That means that if your key is ever stolen, that any key or any object for any tenant can actually be decrypted, which is not good. It's not the best case scenario, but of course it's better than just having no encryption at all. So if you have someone in the data center who just decides to steal one of the hard drives or something like that, it'll just take them a little bit longer, if not impossible, to decrypt that. So a test of this is, if you just upload a plain text file, if you don't have the encrypted object support turned on, somebody gets access to your object storage server, they're able to recover that information quite well, and then if the object is encrypted, there's just no result at all. So that's our object storage encryption that we've introduced earlier this year. And the final feature that I wanted to outline that we've deployed is the OpenStack app catalog. The project is called OpenStack Murano, and it provides an application catalog where users can log into the dashboard and they can deploy an application, however many that you have configured in your environment. There are some pre-made applications that you can go ahead and simply just import. We found that, like most things, if you use a community Puppet module, a community Ansible module, or anything community, you're going to be doing some customization to tailor it to your site. We found the same thing with the applications. So we've tailored these to ours. They're actually quite easy to tailor. And this echoes what David Jericho said earlier about users really only care about the service. They really don't care about the technology. So when you present users, instead of here's a plain virtual machine, instead here's an Apache deployment or here's a WordPress deployment. It makes a larger impact. So the way that these work is you have a quick wizard that you go through. You add in whatever information you would need for the application to start working. This in particular related to storage is that you can have one or more storage volumes attached to the application as well. That happens behind the scenes, so the user really doesn't care much about how it happens. They just sort of give how big they want the volume to be. They size out their virtual machine, and then you can have these other type of customizations. Like this is an example of the MySQL wizard. You can configure it to say, well, I want the volumes to be, or rather, I want the MySQL databases to be backed up to our object storage service once a night. So you can start combining services in this way. So future data storage focused applications that we're looking at, OwnCloud, Spark, and Hadoop. We have quite a number of researchers who would be able to use these. There's several talks going on here about entire sites using a single OwnCloud instance or a single Hadoop instance or things like that. We're an NREN, and we do have quite a large user base, and those user bases are different. They could be researchers, or it could be just a group of people who are in a startup that they're trying to bootstrap an application. So it's not really possible for us to just have one OwnCloud environment because we have so many different uses. So what we're trying to do is provide the ability for users to deploy their own cloud environment in as much of a low barrier way as possible, and then they can start managing it on their own. And the same with Spark and Hadoop. So that's it. Really short and simple of some of the storage things we've been doing over the past year. And thank you.
Thank you, Joe. Is there any questions for Joe here? Yes, here, please.
You mentioned the app catalog, and now it's even more easier to deploy, for example, in an Apache server. What we are concerned about is if we are employing our cloud, then we will have a lot of possibly unmanaged VMs, and this would even make this worse, I think. Did you think about how to?
Yeah, that's true. We do have a good percentage of idle virtual machines in our cloud. Not a good percentage, like 25% is probably significantly less than that. But we also do overcommitting on our cloud quite a bit, and there are definitely some disadvantages to overcommitting, but some of the benefits are that when something is just idle and it's released anything that it's using, it can sit idle all day long and it's fine. We also have times when we need to do a kernel upgrade on the hypervisor, whether it's a security update or something like that. We'll send a notice out to users, we'll restart the hypervisor, and then we'll notice that maybe only 75% of the virtual machines come back. Because those ones are just not in use anymore. So in terms of doing any type of updates to our hypervisors, it's also useful for cleaning out some dead instances.
So the solution is to make hypervisor updates often.
Yes, yes.
Thank you for answering. So, thanks for your talk.